In a lab at the University of Pennsylvania, Vijay Kumar is funded in part by the military to create autonomous drones that don't need external links and, like us, can sense their environment.
What you see on this robot are these two chips here, which are essentially rate gyroscopes. These play the same role as the semicircular canals in the human body located near the ears, which essentially tell us orientation. So the rate gyroscopes that are on board can actually measure these angular velocities at thousands of times a second. This chip here is the accelerometer, and this allows the robot to sense accelerations in the lateral direction. So these are analogs to the otolith organs that measure acceleration in the human head.
When a human pilot feels an unexpected change in acceleration, he knows to adjust the aircraft.
And the robots do exactly the same thing.
The sensors adjust the craft by changing the relative velocities of the rotors and allow the drones to follow a leader with precision.
A fundamental problem in coordinating multiple robots is the ability to maintain formations. What a robot has to do is determine where its neighbors are and figure out what the relative position is, and then monitor that relative separation very carefully. You only need to tell one robot how to move, and the other robots essentially maintain formation by just keeping a specified relative distance. In the figure eight, they come within inches of each other, so they have to combat aerodynamic effects from their neighbors, and they have to have very, very precise control. And all that is done autonomously.
The precision of the robots allows them to do some things more quickly and accurately than human pilots can, like predict the movement and the shape of an object and adjust accordingly.
In terms of acrobatics, I think it'll be hard to beat what a robot can do. The neuromuscular system in the human body, there may be delays of the order of 80 milliseconds to 200 milliseconds before you actually take an action in response to what you see. Well, robots have this unfair advantage. They can do these computations hundreds of times a second. So your delays are of the order of a millisecond and perhaps even less.
In the lab, the drones communicate with a central computer that uses motion capture, an optical system that tracks silver reflective markers on the robots and tells them where they are at all times. But soon it may be possible to cut the cord. And they've already developed another autonomous drone that can go anywhere on its own.
The holy grail is to do all of this without any kind of external sensing, without GPS. And in principle, we can do it. These bigger robots actually rely on observations of external features to tell them where they are in the environment.
This drone carries a laser rangefinder that determines distance to obstacles and a depth camera that reveals 3D information about the surroundings.
They carry on board the processing power, the sensors that are necessary to look at the environment, to reason about the environment. So they can take their relative location and the location of the features to build a three-dimensional map. Well, I'd like to see this technology being used for humanitarian purposes. Imagine there's a 911 call from the building. I think we'll soon have the technology that enables, let's say, 20 UAVs to just swoop through the building and within a minute find out who's in each room and then communicate that to firefighters who are waiting outside. But any technology that you develop, there are always people who are going to use it in ways that the designer never intended them to be.